Let's consider our second class of reversible inhibitors, non-competitive, and see how it compares to competitive inhibitors. First, keep in mind that we're still discussing reversible inhibitors that can have only a temporary effect on enzyme activity. The term non-competitive literally means not competitive, so we might expect it to give results different from that of a competitive inhibitor, and indeed it does. First, it binds to the enzyme in a location separate from the active site, so indeed the binding is not competitive. Since it binds separate from the active site, then it can bind to the enzyme whether the substrate is bound or not. This is represented by the figure here. The substrate is the yellow oval and binds at the active site. The inhibitor is the orange square and binds elsewhere. In this case, we have two different equilibrium dissociation constants. Ki represents the affinity with which the free enzyme binds the inhibitor, and the Ki prime value represents the affinity of binding to the ES complex. This means that there are several equilibria involved, represented in the expression on the right. A true non-competitive inhibitor has no effect on substrate binding, which means that it does not alter the value of Km. However, it does prevent formation of product while bound, even if substrate is present. The enzyme can still make product once the inhibitor is released, but not at the same rate as in its absence. This means that Vmax will decrease. Hopefully you can see the appropriateness of the term non-competitive. A competitive inhibitor lowers substrate affinity, but has no impact on Vmax. This is not the case for a non-competitive inhibitor. Instead, it leaves Km unaltered and lowers Vmax. In this case, since there is no competition with the substrate, we cannot outcompete the inhibitor. We've seen that Vmax is decreased in the presence of a non-competitive inhibitor. By how much is it changed? It is altered by the same factor as the competitive inhibitor, the factor alpha. Alpha has the same significance here, but in this case it is the Vmax that changes. In other words, the Vmax in the presence of the non-competitive inhibitor, the Vimax, is the true Vmax divided by alpha. In this case, the Ki value within the expression for alpha is the dissociation constant for the enzyme inhibitor complex. Now let's see what happens to the Lineweaver-Burke equation. Since Vmax is decreased by alpha, then 1 over Vmax would be increased by alpha. We need to include the alpha term in both the y-intercept and the slope, since the term 1 over Vmax is in both. This alteration of the Lineweaver-Burke equation tells us that both the slope and y-intercept will increase. As we look at the Lineweaver-Burke plot, we can see it is just as we predicted. In the presence of a non-competitive inhibitor, both the slope and y-intercept are increased. Notice, however, that the x-intercept does not change, since the value of Km is the same in the presence of a non-competitive inhibitor. As you can see, a non-competitive inhibitor is in many ways distinct from a competitive inhibitor.